Pleasure to introduce for the first talk of the morning, Terence Tao of UCLA, who will speak on higher Fourier uniformity of arithmetic functions in all or almost all short intervals.
It's a great pleasure to be back here in Montreal, especially on the occasion of Andrew's birthday. I already told some stories about Andrew, but I'll just say one more thing. So when I visited Andrew, actually I visited Montreal in 2006. A great time here. It was a time where Ben Green and I had a lot of success in using techniques of additive combinatorics to attack some questions in analytic number theory. So we've been kind of cocky. Maybe we can tackle these other problems in analytic number theory too. And I remember talking to Andrew and said, "Okay, I got a problem for you." I said, "Yeah." And so he told me about the Erdős problem, or discrepancy of ±1 sequences. And I worked on it before in Montreal, and I realized that it was the key problem was number theoretic, and all our fancy techniques couldn't actually solve it. And indeed, it wasn't until the breakthrough of Matomaki and Radziwill a lot later, which of course you also played a big role in, that problem became unblocked. But yeah, it was a great time. Okay, so I'm going to talk about work joint with Max and Kaiser, and also John Zheng and Yoni on bounds on arithmetic functions. Well, not all arithmetic functions, just the classical ones. So of course you all know what arithmetic function is, just a function on the natural numbers with complex values, and we're going to focus on the classical arithmetic functions. So the divisor functions, the number of ways of writing a number, sum of as a product of k factors, or the Mobius function. Lua function is a close cousin of the Mobius function, or the Mangoldt function. They're all very related to each other by various identities. So the Vaughan identity, Heath-Brown identity, Linux identity, they all connect to each other, and they all have very similar Dirichlet series. They all involve the zeta function. So we have results for all three of these classes, and pretty much anything that has a Heath-Brown type identity, our methods can touch. But for the sake of this talk, I will mostly focus on the Mobius function, but we have results for the other functions too. Okay, so for the Mobius function, one of the guiding principles understanding the behavior is what's called the Mobius student randomness principle, as in the book of Ivanich and Kowalski. So one way to phrase this principle is that if you take an interval, and you could either take a long interval, which means one from 1 to a large number x, or a short interval of some short length h, where the starting point x is big, it's close to it's of size about capital X, and h, the length, is shorter than the starting point. So that's what I call a short interval. So the principle is that if you take a long or a short interval, then for either all such intervals or most such intervals, almost all intervals, like excluding some density 0 set of exceptions, the Mobius function should not correlate with anything structured. So if you take any structured bounded function, so a function on this interval, which is bounded, say, by 1 in magnitude, and structured, which is a very vague term, which I won't really define here. I'll give some examples. Then the Mobius function should have some cancellation when you inner product it with the structured function, that you should get little o of the trivial bound of mod I, which is what you get from the triangle inequality. Okay, so basically this is saying that the Mobius function does not behave like a periodic function or some other structured object. Okay, so this is a very vague but quite useful guiding principle about the Mobius function, that it basically behaves like a random function, despite being multiplicative. So I didn't define what structured means, so I'll just give examples of what I mean by structured functions. So periodic functions I definitely would consider structured. Linear phases, so e of alpha n, e of course is e to 2 pi I alpha n, so linear phases we consider structured. More generally, any polynomial phase, for example, e of alpha n squared, I would consider structured. And then, as we have learned from modern additive combinatorics, there's a wider class of structured functions that are important when you want to do things like solve linear equations, which have these things called nilsequences. So instead of taking a polynomial, taking values in the unitorus, which is what the classical polynomial phase is, you take a polynomial taking values in a nilpotent group, and then you quotient it out to a new manifold. And instead of taking this function e, you take some Lipschitz function on the new manifold. And these give you more general structured functions. You can they're roughly the same thing as bracket polynomial phases, where instead of things like e of alpha n squared, you take maybe e of integer part of alpha n times beta n, something like that. But I don't want to focus too much on the precise definition of these null sequences, but just think of them as more general versions of polynomial phases. I phrase this conjecture, this Mobius principle, in terms of just qualitative decay, just little o, where little o means as the length of the interval goes to infinity. But often you can hope to do better and save something more quantitative. A very typical thing to save is an arbitrary power of log x. And that's usually the best you can hope for if you don't exclude single zeros and stuff. Now, I phrased this principle for the Mobius function where it is the easiest to state. You can also put in the Liouville function and you get basically the exact same principle. If you try to write down an analogous principle for the divisor function or the Mangoldt function, it's more complicated because those functions are non-negative, and you don't always expect this correlation. For example, if f is 1 and you have, say, the Mangoldt function here, then of course you should get some positive thing on the right. There should be a main term. So if you put in some other arithmetic function here, you'd expect the main term, and what the main term is depends on f. But we find actually the most convenient way to actually deal with that main term is for each of these other functions, dk and lambda, you can construct an approximate. It's kind of a type 1 sum type approximate, which we call dk sharp or lambda sharp, which is just sort of the major arc version of dk and lambda, if you wish. What you can do is you just subtract this approximate from dk or lambda sharp from lambda, and then there's a similar principle. Okay, and dk is actually the easiest. So of these three functions, yeah. So I arrange these functions in order of difficulty. So dk is the easiest function to understand, and especially when k is small. So d2 is the easiest function, or d1 of course is trivial, but dk's are the easiest. Mobius is of intermediate difficulty, and Mangoldt is the hardest. Although that's the one that we really care about because it counts primes. Okay. All right. Now, if the interval is really short, there is a small problem that for example, the Mobius function, if you take a really short interval, then just by random chance, it could happen that the Mobius function is just completely all ones or all minus ones. And that is expected to happen once the length gets really small, like less than log x. So for really small intervals, you do not expect discorrelation for all intervals. You only expect discorrelation for almost all intervals, just because randomly you might just occasionally get extreme correlation. But for larger intervals like x to the epsilon, you expect discorrelation for all intervals. In many applications, it's not enough to just get discorrelation for a single function. You'd like to actually get uniform estimates for a class of functions. So here's a typical thing you might want. So for every real number alpha, there's a linear phase E of alpha n, and you may request not just that the Mobius function discorrelates with each individual linear phase for, let's say, for almost all intervals, but even if you take the soup over all alphas, then even then, still for almost all intervals, you can control uniformly the soup, and that's a stronger estimate and more difficult. And this alpha, because you want to control, often this alpha ranges over both like major arc type frequencies, which are close to rational, and minor arc frequencies that are very irrational, and you want uniform bounds on both, and that's often very important in many applications. For instance, you want to use the circle method or something. So let me just give you some examples. Okay, so there are many results that sort of this flavor of that the Mobius function discorrelates with something. So I'll just give you some examples of results that are in the literature, starting with the long interval case, where you're summing just from 1 to x. So for example, the prime number theorem, you can show that Mobius discorrelates with 1, that if you sum the Mobius function from 1 to x, you can get much better than x. So using the classical zero-free region, you can save e to the square root log x. Using the classical zero-free region, and with Vinogradov-Korolev, you can get something slightly better. Of course, with Riemann hypothesis, we expect to save the square root of x, but we can't prove that. If you restrict to an arithmetic regression, so if you're correlating mu with basically a periodic function, then we can't quite save this much because of C equals zeros, but we can save any power of log x with a constant, which unfortunately is ineffective, but that's another story. More generally, not just periodic functions, but long time ago, Davenport showed that if you correlate mu against any linear phase, then no matter what, uniformly in the choice of linear phase, you also save any power of log x. I think this was generalized by Hua to polynomial phases. I didn't say that here, but then later on we generalized to this more general class of nilsequences. And then there's this famous conjecture of Sarnak that, in fact, the Mobius function should discorrelate on long intervals with any zero entropy sequence. So if you have any dynamical system, where the entropy, the topological entropy of the system is zero, and you take any continuous function on that system and any orbit, this Mobius function should discorrelate with any zero entropy system. So somehow it's like the Mobius function has maximal entropy or has high entropy in a very strong sense. Okay. All right. So this is sort of the situation for long intervals. Now, short intervals are harder. Of course, if you can control short intervals, you can average them together and get bounds on long intervals. So and the shorter the interval, the harder it is to get theorems. But we have theorems. So, for example, if you're correlating Mobius with 1, we have some bounds on short intervals. So, for instance, we can get it can save powers of log on any short interval as long as h is bigger than h x to the 7/12. And I'm not completely sure who to attribute this to, but it's some union of these 4 authors. I think Huxley did the Mangoldt function, and and there's various things to do with the epsilon in the later papers. Actually, annoyingly, it's hard to improve the 7/12. So even on RH, you can only get 1/2, and there's no obvious route to get any lower than that. If you stick in a phase like e to the alpha n, this is very nice out of Jean, that you also get discorrelation on short intervals with a linear phase uniformly over all frequencies, which is quite useful. But you have to increase you have to lengthen the interval a little bit from 7/12 to 5/8, which is a little bit. So 7/12 is 0.566, and 5/8 is 0.625. It's a bit bigger. All right. So 5/8, we've not been able to improve this 5/8 with this bound, but a few years ago, Kaiser and Yoni were able to get some bound. So you can lower 5/8 to 6/3, 0.6, which is a little bit lower. But the price you pay is that you don't save an arbitrary power of log x. You now only save a small power of log x. In fact, I think they can even save up to almost a full power of log. Okay, it's because you can there's a trick to restrict to like well factorable numbers, and then the decompositions get a little bit more favorable. So that's for linear phases, and then for polynomial phases, there was a result of Kaiser and Zhuangsheng, which also got discorrelation against any polynomial phase, but they had to make even larger intervals, x to the 2/3, 0.66, which is a bit larger. Okay, so these are the type of results that were known for long intervals, for short intervals, but not too short. Right? It will be somewhat bigger than the next 1/2. But that's kind of, I mean, given that even on RH you can't break 1/2, it's not too surprising that we're stuck somewhere above 1/2. And there's similar results for Mangoldt and divisor functions, but I won't. Well, for some of these results, not for the Matomaki theorem. So now, if instead of all short intervals, you look at almost all short intervals, then it's an easier problem. You have more averaging, and we can shorten the intervals quite a bit. So there's a result. This one actually, I've not been able to locate who first proved this.
Over many years ago, and I didn't know this reference, and he came up to me after the talk to tell me it was he.
Okay, that's okay. That brings you a little closer. Huh? Okay. All right.
It's really It's really Huxley building on Selberg's paper.
Okay.
Selberg did this with the best result known up to then, and Huxley's improvement of that result gave this from Selberg's paper.
Right.
And it was Jean-Louis Nicolas.
Okay. Thank you. All right. So it was due to Nicolas. All right. Okay. But yeah, Huxley did that for the Mangoldt function, I think. But yeah, that's right. But it's okay. All right. Thank you. Okay. I had trouble tracking down that reference. It was an exercise in your book, but that wasn't okay. But okay. But yes. Okay. Yeah. So for almost all intervals of length 1/6, x to the 1/6, you can get discorrelation for the Mobius function. And it's a major open problem to beat that 1/6. That question has like many equivalent forms, including one that, well, anyway. Okay, so this 1/6 was this big barrier for a long time, and then, but there was this famous breakthrough of Kaiser and Max in 2015, where you can actually get any short interval amazingly, like even like log x. Like suddenly you can sort of get all the way down to the shortest possible, but the price you pay is that you only get a qualitative gain. In a quality, well, it's not completely qualitative. You do gain like a log h or something like that if you work it out properly. But yeah, you don't gain this full power of these arbitrary powers of log x anymore. In fact, you wouldn't expect to actually. You know, yeah, like when h is 2. Well, yeah, okay, yeah, so that's a really useful result. Very shortly afterwards, I worked with Max and Kaiser to generalize it a little bit. You can twist the Mobius function by a linear phase, and you get a very similar theorem. But the catch was it was not uniform. So for each fixed alpha, we got a similar estimate for almost all intervals, but the definition of almost all depends on alpha. So we did not get a uniform estimate in alpha, which was kind of frustrating because that would have many more applications. But that's what we could do by generalizing the method. Okay, this was extended more recently by He and Wang. You can replace this linear phase by either a polynomial phase or more generally a no sequence. More recently, still building on the actually MSI program that Andrew and I and others helped organize. In fact, most of the organizers are here, actually. But we did finally get the uniform estimate that we wanted, but at a cost, which is actually a bit frustrating, is that we had to retreat. We couldn't get arbitrary h, which would have been fantastic. H now had to be a small power of x, which actually blocks us from actually the most interesting application. We had quite a complicated proof of this, but it got simplified by Mangoldt Walsh recently. And that was with linear phases, and then also with Teravainen and Ziegler, we also managed to generalize that to no sequences with an even more complicated argument. Okay. Yeah. So okay. So if you fix the numeric, yeah. So what this? In order to fit everything on the slide, I skipped up on the quantifiers. Okay. Yeah. So you fix the new manifold. And you can fix, say, the Lipschitz function, but yeah, you can soup over all polynomial sequences, and that's the analog of souping over this frequency alpha here. Yeah, of course, the decay will depend on the dimension and the nilpotency class of the new manifold, and also the Lipschitz constant of the function. Okay. Yeah, one reason we care about these type of bounds is that if we could get rid of this x to the epsilon. So there's an observation I made a few years ago that if you could actually get this almost all type result, not just for h of size x to the epsilon, but any h that goes to infinity, like log x and so forth. So if you could get a Matomaki Radziwill type result with this twist uniformly over all polynomials, then you get a bunch of useful consequences. You almost get the Charlotte conjecture. You almost get control over all the correlations of the Mobius function, just with the caveat that you have to use log averaging rather than the natural averaging, and you also get a log version of the Sinai conjecture. In fact, these two conjectures are equivalent. So that's something that I've been trying to do for years. Okay, and that's the closest we never get so far. There seems to be this big barrier, actually. All our techniques break down as you approach log x, and log x is somehow, but the log x is the barrier you need to cross in order to start getting these applications. There really seems to be a qualitative difference between intervals of length less than log x and intervals of length bigger than log x. It's a different theory, and so we're missing something, and I don't know what. Yeah, so no, yeah, so the rule of thumb is that if you have a bound for Mobius and which saves lots and lots of powers of log x, then you probably will also get the same bound for Mangoldt. But if you have a bound for Mobius that only saves a little o, that doesn't seem to help with Mangoldt. So, you know, so the analog of the Charlotte conjecture is the Hardy-Littlewood conjecture, and there's no equivalences of this type. I've looked. At least I don't know of any. I would love to have a similar program like this, but Charlotte actually seems simpler, like more attackable than Hardy-Littlewood, because you only need to save a little o, and you don't need to save big powers of log x. All right. Okay, so that is the existing results. So the results that we wanted to present. So we are able on short intervals to improve the previous exponents and get some uniformity. So so this is with Kaiser, Max, and Yoni. We invited Kaiser, Chuancheng, and Yoni. We invited Max, but he declined to join us on this project. Yeah, so we do get uniform correlation of the Mobius with anything. So linear phases, polynomial phases, or most generally no sequences, and we can get down to the Zhang exponent 5/8. So it's the best we can do with current technology. The limitation of 5/8 is that it's not a matter of fancy no sequences. If you take like just n to the IT here, and n to the IT on a short interval, you can approximate n to the IT by a polynomial phase. So n to the IT is an example, roughly speaking, of a no sequence. Then to control that sum, it's equivalent to some fourth moment estimate. Well, you have to control something like a fourth moment with zeta function, and there's a real barrier getting below 5/8. But we can reach that barrier for uniformly for any choice of structured function over here. Similar to what Kaiser and Chuancheng did, if you are willing to Yoni did, sorry. If you only want to save a small power of log x, you can drop from 5/8 to 3/5. And it's the same thing. You can restrict this to Will factorable numbers, and then the decompositions become a little bit better. And because we're saving powers of log x, a big power of log x here, we have a similar theorem for Mangoldt and dk here. But for this result, because we're only saving a small power of log x, there was actually no analogous result for Mangoldt. Actually, for dk, maybe possibly it's still true, but I didn't think about that. And then one special case that's much easier for D2, the standard divisor function, we can actually get down to 1/3, which we're kind of proud of. That we can break this 1/2 barrier, but only for the easiest function, D2. Okay, so that's for all intervals. If you restrict to almost all intervals, so this is work in progress. We are still writing it up. So what we think we can do is that even for Mangoldt, the hardest function, we can actually get a really nice bound where we save powers of log x for almost all intervals, and we can get down to 1/3, which, so Huxley's result for primes and short intervals can get down to 1/6. So we can't get down all that way. There's lots of barriers at 1/3, things that go wrong. We have to start understanding D3 in particular, which we don't understand at all. But we can get down to 1/3 and get a nice result here. And similar results for Mobius and dk. And for dk, we can actually get down to x to the epsilon. So that if you're controlling the divisor function, the kth divisor function, we can get discorrelation uniformly against all no sequences of a certain degree and so forth, down to x to the epsilon, where you save just a little bit over the trivial bound. I think that's the right factor, log k. Maybe k minus 1. Yeah, you're right. Yeah, that's true. Yeah, okay, yeah, that was not quite so interesting with k. All right. Yeah, that's a typo, k minus 1. Thank you, Andrew. All right, he's been doing that to me for 20 years. Okay, all right. Okay, so yeah, so there's some application. I mean, improving exponents, of course, is something that we all do. But actually, this particular result here, where we could 5/2, the fact that we could beat 2/3 actually had a certain technical consequence. We could actually sharpen a certain prime ergodic theorem of Kanagaski, Lamanchik, and Radziwill, on analytic flows, but I won't talk about that here. By kind of now standard methods in high order Fourier analysis, once you control these correlations with nilsequences, you can control these things called Gauss uniformity norms on short intervals, and then you can start counting linear equations and primes, or you can also count linear equations weighted by the Mobius function, and you can get various sort of standard applications, which I will skip here for lack of time. Okay, so I'll just briefly talk about some of the ingredients that go into this type of this work. Okay, so we use what we call the no-sequence large sieve. So one way you can think about the normal large sieve inequality is that if you have a bounded sequence which correlates with a lot of linear phases, you know, e to the alpha 1n, e to the alpha 2n, and so forth, then a lot of these alpha n's must be close to each other. They must collide. That's basically sort of one way of thinking about the large sieve inequality. And there's a generalization well, first of all, you can generalize the polynomial sequences, phases. If you have a bounded sequence that correlates with a lot of polynomial phases, then by messing on Cauchy-Schwarz and the Weil estimates, the Weil estimates, you can show that many of the polynomials phases that they correlate to differ by sort of major arc coefficients that they pretend to be like each other in Andrew and Sound's language. And there's something similar for no sequences, that if a single function, bounded function, correlates with many no sequences, then these no sequences must pretend to be like each other. Now, there's some caveats because no sequences can be parameterized in various ways. You can compose of a homomorphism and change your basis on your new manifold. And you can also multiply by a periodic function, and you can also multiply by a slowly varying function. That's kind of like modifying by frequency by a major arc, or coefficient of polynomial by a major arc frequency. But up to those sort of routine modifications, a lot of these GS must be almost the same. So that there are many pairs of polynomials where one of them is just a transform of the other by some reasonable transformation. And this is a consequence of this equidistribution theory of no sequences that Ben Green and I worked out several years ago, plus a lot of algebra. Another tool we use is a classification of sort of approximately dilation invariant no sequences. So the way we start is the way everyone starts in this business. We use the decomposition identities like Heath Brown to decompose into these things called type 1 sums and type 2 sums. And type 1 sums are fairly well understood. There's also type D2 sums, which show up in some cases. But for type 2 sums, you do lots of Cauchy-Schwarz and so forth. And you find that the enemy is that if your no sequence pretends to be multiplicative, then there's a problem. But if your no sequence does not pretend to be multiplicative, then Cauchy-Schwarz is pretty effective. I mean, this is something that Vinogradov knew ages ago. So what do I mean by sort of approximately multiplicative? It means sort of approximately dilation invariant. So if you take like the standard character NLIT, this is a function which is dilation invariant up to constants. So if you dilate by any shift factor a, you get something which is just a constant multiple of itself. Okay, so the dilate pretends to be like the original function. And you can take on a short interval, you can Taylor expand NLIT to be like a polynomial phase. And so there are polynomial phases that are approximately dilation invariant in the sense that if you dilate by a small amount, you get another polynomial that pretends to be like the original polynomial. And an important step in our arguments is to show that that's basically the only no sequence that has that property. That if you have a no sequence with the property that dilates of that no sequence pretend to be like the no sequence itself, that it must basically come from an NLIT. It must pretend to be like NLIT. And I want to define exactly what pretend means, but I think Andrew can guess. All right. So that kind of handles everything that doesn't pretend to be like NLIT, and the ones that do pretend to be like NLIT, you can handle by classical multiplicative methods, in particular some estimates of Baker, Hammond, and Pence that you conclude. And then two more things. Okay, so as I mentioned before, our previous arguments were quite complicated. We used a lot of really nasty graph theory, but there was a simplification by Walsh, what he called the contagion argument. So basically, if you want to control correlation on almost all short intervals, and you can argue by contradiction. So suppose you are not suppose you do have correlation on many, many short intervals. So on each short interval, there's some nil sequence that Mobius, say, correlates with. Okay, so you have all these different intervals and all these different nil sequences. So to begin with, they don't seem to talk to each other. But the Mobius function is multiplicative. You know that you can take an interval and you can dilate it, and there's some relationship between the Mobius function on the dilated interval and the Mobius function on the short interval because of the multiplicative function properties of Mobius. Now there's a problem because if you dilate by, say, k, it's only the multiples of k inside the dilated interval that directly relate. But hopefully that's some sort of representative sample of the full interval. So because of that, if you have two short intervals which can be dilated to the same larger interval, like if you have one interval where you dilate by k1 and another interval that you dilate by k2 and they collide, you can use the multiplicative properties of Mobius to start, and this no sequence large sieve that I mentioned previously, to start relating the no sequence that Mobius correlates on one short interval has to somehow be related to the Mobius function, the no sequence that Mobius correlates with on the other interval. If you dilate both of them, they must somehow pretend to be like each other. So somehow they have some genetic, they have some genetic similarity in some sense. They don't directly pretend to be like each other, but a certain dilate of one pretends to be like a dilate of the other. And so what Walsh observed is that whenever that happens, that's because there's a parent no sequence living on the bigger interval, such that each of the children no sequences are pretending to be like some sort of sampled version or some sort of downscaled version of this larger interval. So every time you have lots of these little correlations, a lot of them are siblings. They have these parents living on these larger intervals. And then what Walsh realized is that this sort of parenting relation is somehow contagious, that you can take these parents and they themselves actually have to start relating to each other, and they have grandparents on even larger intervals. There are no sequences supported on these larger intervals, which are related in some genetic sense to the shorter intervals. And you can start building up this family tree. You can kind of build up, and eventually you can find this common ancestor. You can find this no sequence on this giant interval, where all the no sequences on these little intervals, which are exhibiting this little correlation, are related by some sort of distant genetic heritage to this giant interval. And then you can start using the results but once the interval gets long enough, you can start using the results on all short intervals that we mentioned previously. And you can show that you don't actually correlate with a no sequence on a really big interval, and then you can sort of descend back down to these short intervals. It actually has some similarity with some of the arguments of Matomaki and Radziwill actually in there. I mean, it's not the same argument, but yeah, this sort of multi-scale type analysis. So that is somehow the main ingredient that allows us to do that. And then the final thing I wanted to say is that to get down to x to 1/3 for D2, so we were initially used all kinds of fancy things, you know, the Kuznetsov formula and automatic forms and a really weird version of van der Kolk and so forth. But strangely enough, for D2, actually, the most elementary methods work the best. If you want to control a sum just involving the second divisor function D2 on a short interval, you can just expand out D2 and just use the hyperbola method. And what you're really doing is that the single sum of a D2 is really a double sum over a neighborhood of a hyperbola. Yeah, so you're just taking some region like this, the pairs of nm where nm, the product nm lies in an interval, and you're summing, I don't know, something like maybe e of alpha nm. And yeah, so you know, so initially we were, well, Max mostly actually was messing around with the automorphic forms to understand this, and you can get some bounds, but actually what we eventually realized is just from the most elementary number theory, in fact, the Dirichlet approximation theorem, you can decompose this hyperbola as long as h is bigger than this 1/3. So there's a critical threshold of 1/3 that if your neighborhood is thick enough, this hyperbola can actually be decomposed into arithmetic progressions. There's a lot of little arithmetic progressions inside this hyperbola. It's a little bit like decomposing the unit-circle into major arcs. Well, I mean, that also uses the Dirichlet approximation theorem in some sense, but you can split up this neighborhood into lots of little progressions, and as long as you can show that on most of these progressions there's a little bit of cancellation, then there's a cancellation on the whole sum. And we understand how to sum things like e to the alpha n on arithmetic progressions, and that turned out to be by far the most effective way to do things. So sometimes the most high-powered technology is not the most efficient. Okay, but maybe that's all I want to say. So happy birthday, Andrew. Oh, okay. Okay, I'll take a look at that. Thank you.
You talked about new lambda and V2.
Mm-hmm.
I'm just wondering if you can do, more arbitrary functions or replace an arbitrary function f by some clever approximate.
Right. So, as I said, basically, we rely very heavily on the Heath-Brown identity. So anything that has a Heath-Brown type of factorization. Maybe smooth numbers, we could do something. Maybe sums of two squares. What we can't do is these coefficients of modular forms. Because we don't have any identity of that form.
James?
Like Jan's estimate, typical case is sort of 4 factors of the same.
Yes.
Like essentially one ridiculous scale.
Yes. Yes.
That's still like
that is the only limiting case. Yes, if you get better bounds. Yeah. There's exactly one obstruction. Yeah, for each of these exponents that we have, we know exactly the one enemy that's blocking us from getting further. Well, for 1/3, actually, there's several enemies, but yeah. We haven't found any new enemies somehow.
So this is a product of 4 equal things?
Yes. Yeah, it's a familiar enemy. Yeah.
Been there.
Yeah. We have some bounds on how big it is. I haven't thought much about what else you can say. Probably they don't all cluster in a very small portion of x and 2x. I'm not sure. There are some results where you can do a little bit of trade-off. So I hit what almost all means. Okay, but you can say that after removing some exceptions, you get a certain quantitative bound on the error. And there are some results where you can trade off. If you accept a worse bound on the exceptional set, you get a better bound on the non-exceptional things, or vice versa. But other than that, we have no structural control on the error.
I mean, if you, like in the new question, suppose you discarded all integers that have prime factors bigger than h.
Mm-hmm.
So there's no sort of unmatched correlation. Every integer in an interval is sort of correlated with any interval.
Right.
So I hope you're doing better.
It's now it's a sparser sequence. So actually, certain Cauchy-Schwarzes become more expensive. The small primes, the small prime factors, they never seem to cause too much trouble. We understand what they do. So we don't really. It doesn't really help to sieve them out. It does something. What does help is to restrict to numbers with a good factorization. We remove numbers that have too many factors or don't have factors in the right places, because then we have these Ramaré type identities in addition to Heath-Brown. So you can decompose things. You can pull out some more type 2 sums and so forth.
You can use Cauchy better.
Yeah, and at the right, you can get sums of the length you want rather than the length that is forced on you. But I don't know how to. Small primes are not the problem somehow. So.
Right, but primes are the big and lengthy interval.
Right. Yeah.
I guess that's the general.
So actually, in some ways, small primes are actually your friend. The reason somehow that mathematical Radziwill can actually control primes, Mobius function on short intervals is because of the multiplicatory properties at very small primes that you can use to pull out certain very, very short Dirichlet series. And if you had the Mangoldt function there, you couldn't do that. It may be that we actually need to keep the small primes in there in order to get results, especially if we just want a little O type gain.
So maybe I should interrupt because our 15-minute break has become a 5-minute break, but is it somebody else?
I had a very short question.
Shall we take a 5-minute break?
Mm-hmm.
Okay. Thanks again.